Now we will begin discussing the topic that is near and dear to my heart, which is that of planets orbiting other stars. These planets, which orbit other stars than our Sun, are known as extrasolar planets or also sometimes exoplanets. What you see here is an artist's depiction of the Beta Pictoris system, which is a star that is known to be surrounded by a lot of gas and dust, and probably most likely in the early stages of planet formation. Here's another artist depiction, although it looks a little pixelated in this slide here, I apologize, of an extrasolar planet and what it might be like to stand on the moon of an extrasolar planet. This is a gas giant planet and an icy moon that you are standing on in this depiction. So how do we know that these planets exist? How can they be detected? Well, there are a number of different techniques. By far, the technique on the ground that has been responsible for the discovery of the most planets for ground-based astronomy has been one which utilizes the spectrum, the light from the spectrum of the star. So how exactly does that work? Well, telescopes receive the light from the star and pass it through a spectrograph. And what they see is the series of lines associated with whatever atoms and molecules and ions are present in that star. What they notice if they do this over a series of images over time is that the lines begin to shift in a predictable way. So we discussed earlier the phenomenon of the Doppler shift, and that is when you have lines that maybe they are lines where you would expect hydrogen to be, but they are shifted towards the redder or bluer end of the spectrum. When they are shifted towards the bluer end of the spectrum, that indicates that the star is moving towards you, and when they are shifted to the redder end of the spectrum, it indicates that the star is moving away from you. Incidentally, it could be that you are moving away from the star, just depending on your frame of reference. But basically what happens with this technique is that you first see the lines, perhaps they're where they should be. And then you look a little bit later and you notice that the lines are no longer where they were, which was where they should be. Instead, now they're blue shifted. And then you look again, the lines are again where they should be. And then you look again later and the lines this time are red shifted. Then again, they gradually go back to where they should be, then blue shift again, and or where they should be, then red shifted again. And you notice that this happens over a regular period of time. What that indicates is the presence of an unseen planet. Due to the force of gravity, we think of the planets as having gravity, the force of gravity exerted on them by the star that they orbit, but it's actually the case that the planets also exert force on the star. And due to that force, the star will move just a little bit. Obviously, it's not going to move anywhere near the amount of motion you see for a planet because the star is so much more massive. But especially with a massive planet, say a gas giant planet, the effect of this star moving is measurable if you look at the spectrum. What happens during this motion, if you are aligned in such a way, if we are aligned in such a way with this star that we can notice it, then when the planet is traveling away from us in its orbit, then the star is being tugged so that the light is blue shifted, it's heading towards us. And then just the opposite occurs in the other point of its orbit, where the planet is moving one way and the star is moving away from us. And so we see this pattern of lines in the spectrum, which maybe they correspond to hydrogen or helium or some other atom or molecule, and they are periodically shifted from blue to back where they should be, to red, to back where they should be, to blue, and so on and so forth. This indicates that something is causing the star to regularly move towards us and then away from us. And so that's a sign that a star could have a planet orbiting it. What we're able to determine from measuring how these lines move is both the period of the unseen planet and also its mass times a certain angle. Remember, I said it has to do with how the system is aligned to your vision. So we can determine something about the planet's mass, but not exactly, because we don't know the orientation of the way the system appears. It could be that we are looking at it edge on exactly, but we might be at a slight angle. Okay, so what do I mean by that? I mean that this angle I is the angle between the almost like the pull of the star and where the planet actually would be. So if it was the case that we had I of 90 degrees, then that would be a right angle. And if you know anything about your trigonometric functions, then the sine of 90 degrees is equal to 1. And so if we have exactly 90 degrees for our inclination angle, then we know the exact mass of the planet. But in most cases, all we can do is estimate because we don't really know that sign a priori when we are observing the system. Another way we can detect planets is through actually marking down this wobble that I'm referring to due to the force of gravity pulling on the star from the planet. And how that works is, again, you take a series of images, but this time on the actual image, you try and measure the way the star moves and how it appears to wobble over time. This technique was one of the first techniques tried to try and detect extrasolar planets. And the unfortunate thing about it is that it really requires a very massive planet to create enough of a pull for us to notice any kind of wobble. And also the star needs to be relatively close to us, nearby, and the farther the star is, the more we will notice, the farther the planet is from the star, the more we will notice this effect. But if we are able to measure it, we can determine the period and that inclination angle plus the mass of the planet. Very few planets, by the way, though, have been discovered with this technique. The second most the other technique that is probably second most effective in how many planets have been discovered using it, and probably now actually has the most planets to this technique due to the fact that the Kepler telescope is in orbit using this particular detection technique. But even before Kepler was launched on the ground, this technique was responsible for a good number of discoveries. This is something called the transit technique. This technique, the only downside to it is that it has to only occur with planets that are just perfectly aligned to our vision. Because what we're looking for is we're looking for a planet to pass in front of the star at some point during its orbit. Now, depending on how the star is aligned and the system is aligned, this may not happen. We may not be aligned in just that particular way that the planet will block out a little bit of the light from the star during some point in its orbit. But if it does, if it is aligned this way, then this dip in brightness is actually detectable. It's a very, very small effect because the planet is much, much smaller than the star. But when it crosses in front between us and the star, it does block out a little bit of the light of the star. Think about a bug flying in front of your street lamp or something. You may notice a little bit of dimming when that occurs if you're looking right at that time. It is difficult to do this, but it can be done. And when it's done, we are able to figure out what the radius of the planet is, not its mass, but we can determine its radius. And furthermore, we can tell that if this occurs, then that must mean that the inclination angle of the planetary system has to be very, very close to 90 degrees. We can take it to be approximately equal to 90 degrees. Because otherwise, the planet would not cross in front of the star if it was dipped at any kind of significant angle from 90 degrees. So based on that information, we can then go back to the people. So this is the picture you have in mind. It's only going to cross in front of our eyes if that eye is equal to 90 degrees. But anyhow, based on the fact that we have now found a planet using this technique, we can go back to people who have a spectroscope and can take measurements of the spectrum of the star. This is the spectroscope method is also called radial velocity technique. And combining what we know with what the spectrograph can detect with radial velocity, we can then give the exact mass of the planet because we are taking I equal to 90 degrees. And if you recall what I said earlier, sine of 90 degrees is just 1. So now we can take that to be the exact mass of the planet. And once we know, and actually incidentally, once we know the mass of the planet, since we've already determined its radius, that interestingly will tell us something about the density of the planet, which from there we can infer what the planet may be made of, whether or not it's a gas giant planet, whether or not it's more likely to be a rocky planet, and so on. So let's look at how telescopes actually do this transit technique. And this I'm a little biased towards because this is what I did my research in. And in fact, the picture that you see here is an image from my research. And it's just an image of a particular star with what looks like a series of bullseyes surrounding it. These indicate measurements. This is a technique called aperture photometry. So inside the green inner circle, you see that roughly surrounds the star completely. So what the computer does is it says, okay, well within this circle, how many pixels do I have of light? And then it compares that to the outer circles where there is basically no light occurring from that star. And from that comparison of the background noise to the actual star's light, you can get a pretty good measure of the star's brightness. Okay, so this is the star brightness, this is the sky background brightness, and so from those two things, we figure out what the brightness of the star is. And then over time, we compare that to a reference star. The sky may change due to seeing or humidity changes, temperature changes, things like that. As we progress through the night, the sky's brightness may change. But as long as a star is pretty stable, then its brightness should not change. So if we see that one star gets a little bit dimmer and another star also gets a little bit dimmer, we can assume, okay, well that has to do with maybe some effect of the sky. But if we correct for that and we notice that the second star, even though we corrected for that, it's still getting much, much dimmer or much, much brighter than the other stars that were the reference stars that we're comparing it to, then something special must be going on with that star. And so if we plot these relative brightnesses over time, we can then see if there's any kind of dip in brightness. So recall this picture here where over time the brightness the star starts out a certain brightness, and then when the planet passes in front of it, you see that the brightness dips down, and at the point where the planet would be completing that pass in front of the star, then the star becomes bright again, just as you might expect. So this is the pattern that you see in the graph on the right, and this is actual data that that I helped gather for a collaboration which was studying a planet called HD 80606b. and this was an international collaboration across the globe. Our data points are basically only the dark circles that you see towards the right of the graph. Some of the other colors or open circles represent other observatories, and we combined our data together to get this nice graph. That is because this particular orbit takes 16 hours to take place, and so one particular observatory would run out of dark hours before they would get an entire transit of this star taking place. So we combined our data and collaborated in that way. The research group that I formed at the University of Pittsburgh, I dubbed STEP UP, which stands for Survey of Transiting Extrasolar Planets at the University of Pittsburgh. And it's a student-run research team, mainly undergraduates participating. As far as I know, I've been the only graduate student to work on it as the founding member. And what we do, though, is we use the Allegheny Observatory. We use a 16-inch Meade telescope there, which is pictured in the upper left. The middle image is an image from the HD 80606b campaign, whose data is plotted to the right. But if you end up transferring to Pitt, or if you are a Pitt student yourself, just taking this astronomy class at WCCC as a summer course, you are actually welcome to be involved with the Step Up group. It's open to students of all majors. So if that's something that you're interested in, I would recommend you get in touch with Professor Michael Woodvasey and see if he has any openings available for you to participate in that sort of research. But some planets that we studied with the Step Up team, some examples basically. Trace 2b is a typical, what we call in the field, a hot Jupiter. Why we call it a hot Jupiter is because it is about the size of Jupiter, actually in this case a little bit larger than Jupiter, only it is orbiting very close to its parent star. Trace 2b, for example, orbits at 0.0367 AU, so it is like very close to its star, closer than Mercury would be to the Sun. It only takes less than 3 days for it to complete one orbit. Being that close to a star, and incidentally this planet's parent star is very comparable to the Sun in size and temperature, it would be a very hot world rather than what we think of when we think of gas giant planets, which is cold worlds like Jupiter and Saturn. So it's something the size of Jupiter, only located inside where Mars would be if this were the solar system. Okay, so this particular exoplanet is within the Kepler field, so it is something that the Kepler telescope has also been able to study, and there's lots of information on this particular planet. This is an image that was taken from my data. On the left, that's some image from my data. On the right is a sky map, which allowed me to identify which star was Trace B. And so that is indicated with sort of a red cross on the right sky atlas. And on the left image, I have it circled, identifying this as the same star. And so when I was an undergraduate, I didn't have as sophisticated programming techniques. Instead, I used a GUI software called Mira, I'm not sure how you pronounce it actually, that allowed me to kind of click on the star and take a measurement of its brightness, and then I would do that for each of many, many images for the star itself, the target star, and for two reference stars for comparison. So this was a very cumbersome way to do the aperture photometry and look at the brightness of these stars, but it did work, and I was able to get a light curve like this. This, however, is the same data run through some code that I was later able to program as a graduate student. And so this transit took place over 2.4 hours, which, if you go back to what we said about how long it takes the planet to complete one orbit. It only takes 2.47 days, but that period of time where it's actually in front of the star is much, much less. It's only about 2.5 hours. The first exoplanet that I studied was one called Exo2b, and this one is also a Jupiter-sized planet and a hot Jupiter located very close to its parent star, very similar distance to Trace 2b, and a very similar period of its orbit, about 2.6 days. What's interesting about some of these hot giants is that, or hot Jupiters, I'm sorry, is that their radii are sometimes larger than we would expect them to be. They're inflated in size. Could it be that this is due to the heat of the star? Possibly. It's difficult to say for sure, but based on what we know of, for example, Exo2b's mass, we wouldn't expect its radius to be quite as large as it actually is, because you see the artist's depiction up here. When you look at the size and radius of the two, Jupiter and Exo2b, they're very close in size, even though the mass is only about half of Jupiter's mass. So here's one of my very first images of studying exoplanets. This is where I identified Exo2, the star, in my image. And these are the results of my data points. You see that I was only able to obtain the beginning part of the transit. I think I ran into bad weather and was unable to complete the entire transit, but you see that things are getting dimmer here, indicating that the planet was starting to pass in front of the star, and then I sort of ran out of time to get the entire transit in. And so finally, the third planet that I've been most involved in was the HD 80606b collaboration, which we talked about earlier. Here's another of our images with the star, the target star circled here. Interestingly enough, the star that's very close next to it to the right is HD 80607, and when you see two stars close together like this, you cannot really generally assume that they are associated with one another. It could just be, the way things are aligned to from our perspective. But in this case, HD 80606 and HD 80607 are associated with each other. They are what we call a visual binary system, because we can actually see the two visually separately, and they do orbit each other, which makes an interesting effect for the planet HD 80606b. These two stars are very similar in size and brightness, but because of the gravitational perturbance of that nearby HD 80607, HD 80606b, the planet's orbit, is on a very eccentric orbit. It's very elongated, and it goes from, at its farthest point away from the star, around where the Earth would be if this were the solar system, to inside Mercury's orbit at its closest approach. And it just so happens that this is one of the few stars that, few exoplanets that what's called a secondary transit was observed before the primary transit. A secondary transit is when there's some residual brightness due to the planet itself, and when the planet passes behind the star, instead of the planet blocking some of the star's light, the star blocks some of the planet's residual light. And so it's very, very, very difficult to detect this. It is most easily detectable in infrared, because that's where the planet is the brightest instead of in visual light. But this particular planet was discovered to have this secondary transit first. And then it was predicted that, hey, maybe since it exhibits the secondary transit, maybe we'll be lucky enough to catch a primary transit, a regular transit. And eventually it was found, the primary transit was found to take place as well. And another interesting thing that just by chance happens to be true is that while this planet is transiting the star, it just so happens to be the point in this planet's orbit where the planet is quickly approaching the star, its closest approach to the star. And so the planet is going through probably a very rapid heating of its atmosphere. The inset that you see here that's numbered 1 through 6 is a computer simulation of what is thought to be taking place as this planet is going through this rapid heating due to becoming closer and closer to its star and sort of plummeting in towards it. Remember, we talked about comets, and as they plummet into the inner solar system, they release so much gas due to all this heat and solar wind. So a similar thing is thought to be happening to HD 80606b, where it's rapidly heating up, and this is causing probably crazy things to happen in its atmosphere and shock waves occurring across the atmosphere. So I don't know if any of you happen to catch the National Geographic special Storm Worlds, where they covered our studies of the HD 80606b campaign. There was like a brief little snippet where I got to say a few words in there, but the bad thing about some of these popular science programs is that they sensationalize things, and so they made it out to seem as though we were observing the storm on this world taking place, and really we were not. We were simply observing the transit of the star taking place. So in case you've seen that, I just want to explain that it's not quite as cool as they made it out to be, although I still think it's pretty cool. So here's the data from the various observatories. Our data, the step-up data, is marked here with an arrow. It's indicated as AO for Allegheny Observatory. And you see that really we were kind of crucial in this collaboration because we got a lot of the data during the dimmer part of the star, when the planet was actually in front of the star, and then also when the star was making its, was leaving, and when the planet was leaving that point and the star was then brightening up. We have a lot of data towards the end of the transit there. So using our data combined with everyone else's, that's when we were able to produce this really nice graph that's got this really beautiful light curve displayed in it. And this made it to a publication in the Astrophysical Journal, which was called Ground-Based Transit Observations of HD 80606b. So another thing that STEP-UP does is follow up on unconfirmed planet systems. So all the ones that I've mentioned before had already been discovered. We were just following up and catching some of these transits when they were predicted to take place. But we can also follow up on what are known as planetary candidates. So things that are orbiting stars, but we don't know yet if they are actually a star or if it's maybe a brown dwarf, which is an object larger than a star, or perhaps it's even just it's a binary star system. So we need to figure out if these are actually things and confirm these discoveries, or maybe it was just a mistake. So we follow up on a project which is called MARVELS as part of the Sloan Digital Sky Survey, and they give us planetary candidates, and then we study them on nights that it's conducive to do so. And so here are some graphs of our data, and the actual locations of these stars are kept confidential since they are unconfirmed systems. But so far, at least until I had finished my master's degree, we had not been able to uncover any confirmation of an actual planet. We were able to kind of confirm the presence of a brown dwarf, but as you see here, we see nothing but null results here in these graphs. They are basically saying the light of the star is roughly constant through time, through the periods of time that are depicted here. So I mentioned some of the characteristics of extrasolar planets, but the interesting thing about the characteristics of extrasolar planets is that in some ways they are similar to planets that we're familiar with, but in a lot of ways they're very different. Perhaps they orbit very close to their parent star, as in a hot Jupiter, or perhaps they travel on a very eccentric orbit like HD 80606b. And so to actually find an Earth-like planet orbiting in this special place where life can exist is a very difficult task. Kepler is out there doing that, looking for that Earth-like planet right now, and it has a few that that could plausibly be somewhat Earth-like, orbiting near what we call the habitable zone, where life could plausibly exist, and roughly the size of Earth, although most of the ones that you've seen on the news have been a little bit bigger than Earth. So really we don't have an exactly true Earth analog that we've found yet, but Kepler, that's its goal, and there's a lot of data that has not yet been sorted through, so I would not be surprised if in that data there is some kind of Earth analog that will be confirmed in the upcoming year or so. Whenever we're looking for known planets to study or candidates to study, a good resource that astronomers use, or that you can just use if you're interested in learning something about these planets, is something called the Extrasolar Planet Encyclopedia. And on there, there's a catalog of all the known planets. This is out of date. This screenshot is from about 2.5 years ago. And so the number of known planets is upwards of 700 or more by now. But as of 2010, the end of 2010, there were over 500 known planets, and you see how some of these were discovered. I didn't go over every single detection technique, but you do see that most of them were discovered by the radial velocity. That's the method that uses the Doppler shift in the spectrum. But then a significant number were also discovered via the transit method that I utilized. So this is a nice resource, and if you actually click on a particular planet, you can learn about what size it is, how far away this planet system is, and things like that, when it was discovered. You can even click on it, more information, and it will tell you some articles that were written about it, scientific articles that have been written about it. Once I've picked out a planet, say it's XO2b, then I use another resource called Transit Search. Even even if you're just into amateur astronomy and you have a way of photographing your images, you can go here too and find out when these transits are predicted to take place, and you can plan your observing around that so that maybe you can catch a transit too. So you can explore some of these links at your leisure. They talk a lot about extrasolar planets and how we detect them, new discoveries and whatnot. So yeah, just have fun with it.